Welcome. The title of this talk is BPNAS, a Bayesian Progressive Neural Architecture Search. So the objective of NAS is to automate designing of neural networks, and the traditional NAS methods usually use very expensive approaches such as reinforcement learning, which is not scalable in practice. Differentiable NAS provides an alternative to those approaches, which is scalable and which introduces differentiability in order to scale the algorithm to larger datasets. A brief schematic of the differentiable NAS is as follows. So this approach is a cell-based approach. The cell is a direct acyclic graph or DAG. We introduce a super network where we have in each edge of this graph multiple operators, and these operators can involve multi-layer perceptrons, convolution nets, and such architectures. And based on this approach, we train these operator weights, and finally, we select the operators with maximum operator weight. So the differentiable NAS objective function is as follows. This is a bi-level objective function which minimizes the training loss with respect to the network weights and biases. And then given those weights and biases, it minimizes the architecture weights, which it does on the validation dataset. And so if you can see here that the loss is completely differentiable with respect to its parameter, and hence it is highly scalable. We propose a Bayesian framework which have this hierarchical form. Here, the most important thing is we introduce this parameter gamma, which essentially introduces sparsity. And we set the prior of this gamma in such a way that it forms the mode at the parameter space where the modulus of gamma is equal to 1 in each edge. So that means in each edge, we are enforcing that we have only one operator. So our objective is to learn the map estimate of the parameters. It is difficult to find this map estimate because our objective function, which is the posterior distribution, is a combination of discrete and continuous random variable. So we devise an algorithm which progressively prunes out less important operators based on the operator weights. Our algorithm is as follows. Here, the most important part is the pruning criteria. So we update the weight and biases by stochastic gradient descent. And after each update, we calculate this L2 distance between a randomly drawn Dirichlet random variable and compare it with an uniform distribution. You can see the Dirichlet random variable has the parameters as the architecture weights. So it essentially computes how far is the weight vector from a uniform weight vector. And if it is far enough, it prunes out the unimportant operators. Then after learning the architecture, we restart this algorithm by randomly sampling an edge and reforming the supernetwork on that edge. We do this n times in parallel to build an ensemble of architecture. On the right, we show an example of this in this NASBench 201 dataset. Here we can see that the blue architecture, which is an outcome of the previous algorithm, has in its one Hamming distance away ensembles the Oracle architecture, which is the best in the NASBench 201 space, which is marked by red. Here are the results of our approach in architecture search experiments on the popular NASBench 201 search space. Here we show results on 3 benchmark datasets, the CIFAR10, CIFAR100, and ImageNet. We observed in all the dataset, BPNAS is competitive with the state-of-the-art method, the DRNAS method. But we observed that BPNAS is converging to a good architecture in a very few epochs. Or in other words, it is highly efficient in finding the architecture. Here are the results for architecture ensemble. Here we compare BPNAS with state-of-the-art neural ensemble search methods. And we can see that in all the cases, the BPNAS produces the highest test accuracy. This is all for this talk. Thank you for listening.